Exponential Models Bookwork, page 1. So we're going to start with a new unit now, and the first thing we're going to do is we're going to get familiar with the exponential function, which you might have heard that word from exponential growth, which means a growth that gets bigger and bigger until it just becomes overwhelmingly large. Okay, so we're going to take a look at some of these functions. So for the first one here, it asks us to graph a function. Now remember, in math studies, when they ask you to graph something, don't panic. It just means that you're going to put it in your calculator and see what it looks like. So in this case here, we basically have y equals 2 to the x power. So if we put that in the calculator, we're going to do that with the y equals screen so we can graph it. And we're going to put 2 caret x. And then we're going to graph. Okay, that looks like exponential growth right there. It's going up, up, and then it just keeps going up at a higher rate until it becomes overwhelmingly large. Now, to put it in our own grid, it's better if we look at it as a table instead of a graph. So we go to second, graph. And what's interesting with the exponential function is not only the positive values of x, but the negative ones too. So we're going to go back a little bit to see some other values of x here. So we can see that like negative 3 happens to be 0.125, negative 2 happens to be 0.25, and negative 1 happens to be 0.5. So negative 1 or 0.125 and 0.25 are kind of small to be graphing on this small grid, so I'm just going to put the negative 1 value first. I'll put negative 1 comma 0.5, and then I'm going to put some of the other values, 0 comma 1, 1 comma 2, and 2 comma 4. You can see that there are no negative y values here. So I'm going to put an x-axis and a y-axis. The x-axis, I'm going to go ahead and put it down here because since there are no negative y values, there's no point in drawing the bottom half of this curve. And then I'm going to put the y-axis about here. Okay. Then I'm going to graph this function in red. So negative 1 comma 1.5, or negative 1 comma 0.5 is right there. 0 comma 1 is right there, 1 comma 2 is right there, and 2 comma 4 is right there. And the next one, according to this table, is 3 comma 8, so I can put that one too. And then I'm already going off the edge of the page, right? So if I was to connect these with a curve, it would look basically like this. Okay? So yeah, I can see how that is exponentially growing. Some of these special values would be like this value, and this value. These values are maybe easy to calculate by hand. For example, if we want to know this middle value here, we would put 0 in for x. 2 to the 0 is always 1. Okay, there is a famous EAC teacher who always said, todo número elevado a zero é sempre So in memory of her, we'll use that here. So whenever you put an exponent of 0, you're going to get 1. What about 2 to the 1? What if x equals 1? 2 to the 1 just means you're going to multiply 2 times itself one time, which is just 2, right? So that's why you get this value here, which is just 2. What if you put x equals negative 1? If x equals negative 1, that's 2 to the negative 1, which means 1 over 2 to the 1, which means 1/2 or 0.5. Okay, so that would be this value here. So those are some special values of the exponents that are quite easy to calculate. Now let's do this one here. It's 6 to the x. Okay, 6 to the x. So we're just going to go to y equals here. And instead of 2, we're going to put 6. And then we're going to graph it first just to see what it looks like. It looks quite similar. And then we're just going to change the table so that we can program, or we can put these numbers into the grid. So we got, the negative 1 comma 0.166 is not easy to graph, so it's just a small number, right? And remember that if we put 6 to the negative 1, that would be 1/6. So if we wrote it as a fraction, maybe it looks a little bit more familiar. So negative 1 negative 1 comma 1/6. If we put 0 in here, it would be 1. If we put 1 in here, it would be 6. And if we put 2, it would be 36. That's already off the screen. So let's graph that. Okay, so negative 1, 1/6 would be very small right there. 0, comma 1 would be right there. 1, comma 6 would be there. So this is an exponential curve that goes up very quickly. Okay, finally let's do 8 to the x, and this will go up even more quickly. So we'll change the 6 to an 8. We'll just go look at the table and don't even need to look at the graph. We're just going to copy some of these numbers off of here. So we got negative 1, comma 0.125, which is 1/8, 0, comma 1, and 1, comma 8. So negative 1, comma 1/8 is that point here. 0, comma 1 is this point here. And 1, comma 8 would be that point there. You notice that it's always intersecting the y-axis at y equals 1. And that's always going to happen as long as you're in this form here, where you don't have a plus 7 or some other value added to it, okay? All right, so those are, let me erase that because I drew it so crooked. Now let's move on to number 4. These are a little bit trickier because you can see that the base of this exponent, okay, the base of the exponent is a fraction, okay? So remember what we're doing here when we have an exponential function is you are multiplying the base times itself multiple times. So let's say that I put 1/3 to the 3rd power. That would mean that I'm doing 1/3 times 1/3 times 1/3. So you can do that with any kind of number, even if it's a fraction or less than 1. The only thing you're not going to do that with is a negative number in this case, okay? And we'll talk about why you don't do that later. Okay, so in this particular case, let's put into our calculator a base of 1/3, and then we got the exponent of x. And let's look at the graph first. This is going to look a little bit different than the first 3 we did because, as you can see, instead of exponentially growing, it's exponentially shrinking. This is called exponential decay when it goes down. So let's pick out a few points from the table so that we can graph it. And now you can see that the negative values of x are the ones that have the larger values of y, and then when we go on the positive values of x, we can see that the y values become very small, so they're kind of hard to graph there. So let's take the values for -2, -1, 0, and 1. Those are the ones that probably we're going to graph on our grid. So -2, comma 9. -1, comma 3. 0, comma 1. There's that 0, comma 1 again. 1, comma 0.33, which is 1, comma 1/3. That makes sense, right? Because 1/3 to the 1st power is equal to 1/3, the base itself, right? You notice that if you do 1/3 to a power, you're multiplying 1/3 times itself many times. So make sure that you always put in parentheses because the power is going to apply to both the top and the bottom. Okay, so let's graph that. I'm going to make a x-axis here, y-axis here, and I'm going to graph some of these points. Negative 2 comma 9 is here, negative 1 comma 3 is here, 0 comma 1 is here, 1 comma 1/3 is here. So it looks kind of like that. Let's do 1/5 to the x. 1/5 to the x. The table. So negative 2 comma 25, that's pretty big. I'm not even going to write it down. It's off the edge of our screen. Negative 1 comma 5. 0 comma 1. There's that 0 comma 1 again. 1 comma 0.2. 0.2, remember, is the same as 1/5. Okay, so let's graph those 3 points. So we got negative 1 comma 5. We got 0 comma 1, and we got 1 comma 0.2. Okay, that's what that looks like. Okay, so when you have a base that is less than 1, you get a shrinking function or a decaying function instead of a growth function. Okay, here are the last 2 problems. These are kind of similar to what we've already seen, except there's some complications here. Do you notice that there's a multiplier in front of the base and the exponent, and there's also a number that is added to it? Okay, so let's put that in the calculator, and you're going to have to be careful about your parentheses here. We're going to put 3 parentheses, 2 parentheses to the x, just like they have it here, plus 4. Let's graph that. Now, one thing I notice is instead of being kind of glued to the x-axis like it was before, now it's floating. Okay, so you may remember in the investigation that if you have a plus 4 here, that it kind of raises the value. So this is what we call an asymptote. It's a horizontal, imaginary horizontal line that the function gets closer and closer to, but never touches. Okay, so the asymptote here would be at the height of 4. Okay, and you notice that here there is a 4. Okay, let's look at the table to get some points here. Okay, so for this function here, some of the interesting points that we can graph are negative 1 comma 5.5 and 0 comma 1, no, 0 comma 7 and 1 comma 10. You notice that for this graph, it is not 0 comma 1 any longer. And the reason why is because the 2 to the x, 2 to the 0 becomes 1, but it's multiplied times 3 and then added 4. So you end up with 7 instead of 1, right? So the only reason why you're going to have 0 comma 1 always is if you have a simple function that has a base and exponent, it doesn't have a multiplier in front, doesn't have something added here like we do here. Okay, 1 comma 10, we wrote that down. What about some of these? So if we go up here a little bit, let's get maybe like, do you notice how like some of these negative values, it gets closer and closer to 4? So we can see that the asymptote is really 4, because if we go, oh, look at that. If we go to negative 16, the calculator can't even like show that this is 4.0000. It's smaller than 4.0001, right? It's not actually 4. The calculator just has a problem showing that it's actually, you know, just slightly above 4. Okay, so let's graph this one here. This is trickier, right? But all these values are positive, so we'll use the same strategy as before, where we will put the x-axis exactly on the bottom of the grid. And then 1 comma 10 would be this point here, 0 comma 7 would be this point here, negative 1 comma 5.5 would be this point here, and then like we said, the asymptote, which is, the asymptote, which is at y equals 4, like we saw, is like right there, right? So we're going to draw a function so that it approaches the asymptote. Okay, and did you notice that up here in the instructions it says to write the equations of the horizontal asymptote? Okay, now for all the ones we've done so far, the horizontal asymptote, we didn't even think about it because the horizontal asymptote was on top of the x-axis. And when the horizontal asymptote is on top of the x-axis, the equation is just going to be y equals 0. Okay, the asymptote equation is always going to be y equals 0 if it's on top of the horizontal, if it's on top of the x-axis. And you may say, why wouldn't it be x equals 0? If it's on top of the x-axis, wouldn't it be x equals 0? Well, think about some of the points that are on the x-axis. I'm going to identify 2 or 3 points and you'll see the pattern. Like, for example, one of the special points that's on the x-axis is 0, 0. That's 0, 0, right? Another possible point would be 1, 0 right there, right? Another point would be 2, 0 right there, right? All three of these points are on the x-axis, but do you notice that the 0 value is always the y-coordinate, not the x-coordinate? So when you identify the line, which is the x-axis, you actually identified it as y equals 0 because the y value is always 0 and the x value is always different. So y equals 0 says it's a horizontal asymptote at height equals 0. Okay, so all of these just have an asymptote of y equals 0 that we've done so far, including this one. But this one here, we can see that actually the y asymptote, or the horizontal asymptote, is y equals 4, right? And the way we can find that is we can just look at the calculator, and if we go up far enough, we can see that it approaches and gets very close to 4. Okay? All right, now finally, there's this complicated one here. It's negative 2, 4 to the x minus 1. So let's change what's in the calculator. We'll put negative 4, parentheses, oh, negative 2, sorry, parentheses, 4, parentheses to the x minus 1. Okay, and then we're going to look at the table for that. We'll get closer to x equals 0, which is a little bit more interesting. Okay, and there we see that, okay, so we're going to write down 2 or 3 values here. One of the values is we're going to write 0, negative 3. 0, negative 3. Another value we're going to write is 1, negative 9. And another value we're going to write, ooh, negative 33, that's too big. Let's go up a little bit. Do you see how when you get to the negative values now, it approaches an asymptote, which appears to be getting very, oh yeah, it got to negative 1. So for this particular case, the asymptote equation is a horizontal asymptote, and the equation is y equals negative 1. Coincidentally or not, that matches the negative 1 here, just like y equals 4 matches the 4 here, right? Okay, so now this time, do you see how all the y values are negative? So what I'm going to do this time is I'm going to put the x-axis up here and the y-axis here so that I can graph many negative y values. So 0, negative 3 would be the first one. 1, negative 9 would be the second one. And then we know that we're going to approach the horizontal asymptote actually is at y equals negative 1, not y equals 1 or y equals 0. Okay, so there's y equals negative 1. We're going to approach that line as we go to the left. Okay, so it's kind of interesting because this exponential function is upside down. And the reason why it's upside down is this negative sign right there. The negative sign right there makes it upside down. But for most problems in math studies, you don't really need to remember every single detail about what the negative signs do because you can always put it into y equals to see exactly what the graph does, okay? But if we look at the graph, we're going to see that what we did here matches it, right? We see an intersection right there. and we see a horizontal asymptote here, and it goes down, right? But if you want to see specific points again, do second table. Okay, that's it for this video.